So let's continue our discussion with this problem. We know first that we came up with a relationship that gives us the velocity of a fluid particle based on its distance from the center of the disk. We came up with a second relationship that gives us the velocity of the fluid particle based on its distance from the bottom. Now, before I move on, are there any questions with these two formulations?
No, sir.
Okay, so if there are no questions, then we can start to actually apply fluid stuff, or fluids principles. d over dy is the rate of change of the velocity with respect to this depth, this distance from the bottom. And we know that for a linear velocity profile, that du di is simply equal to the maximum velocity divided by the thickness. If it makes it easier to remember that a slope is equal to y over x in a linear equation. Therefore, we have our y value, which is our u max, and we have our x value, which is our y. I'm very confusing because we're calling our xy, but you can treat them as independent and dependent variables. Okay, so our du dy equals 30 times radius divided by 150 millimeters. Now let's start to use standard SI units. Okay, so if we're going to measure this radius, this distance in meters, then we should express this thickness in meters as well. So what I'm going to do is I'm going to express this 150 in terms of meters rather than in millimeters. So I'm going to have 30R divided by 0.150 times 10 to the negative 3 meters. And that's my rate of change. That is my du over dy. That is my velocity gradient or my strain rate for this fluid. Now, if I know my velocity gradient, right, and I know my viscosity, I should be able to calculate my shear stress. Because if I can calculate my shear stress, then I can use my shear stress to calculate my torque, okay? So let's go ahead and do that. Let's first calculate our shear stress. We're gonna apply Newton's law of viscosity. This is the law for Newtonian fluids. And we're gonna see that applying this law, we will get an expression for shear stress. So we get that the shear stress at a point in a fluid is equal to its viscosity. And do we know the viscosity of oil? Yes, it was given to us to be 4.428 Pascal per second. I'm going to write Pascal as newtons per meter squared. Okay. And now if we multiply our viscosity times our strain rate, then we get our shear stress. So our strain rate we see is 30R divided by 0.15 times 10 to the negative 3 meters. Now, can somebody solve this expression for me? 30 divided by 0.15 times 10 to the negative 3?
I got 200R.
200? Okay.
Anybody, please feel free to correct me.
I mean, if that's what you got, can somebody please double check that value? Remember that we want our units to be consistent. So we got 30, yeah?
I had 200,000 since it's to the negative 3 on the bottom.
Okay, so this, Logan, this negative 3, right, is gonna add, increase our number by magnitude of 10 to the power of 3, right? So it'll be 200 times 10 to the power of 3, is that correct?
Yes, it looks right. I was looking at the top one.
Okay.
Yours looks like one big M.
I understand. Yes, no, that's absolutely right. So 200 times 10 to the 3R is our strain rate. So we now multiply our strain rate times our viscosity. So we get 0.428 newtons per meter squared times second times 200,000. So 200 times 10 to the power of 3 R. What does that give me? If I multiply 200 times 0.428 and then elevate it to the power of 3, I mean, just multiply 200 times 0.428. So twice of 428 is 856, right? And then we just need to apply our number. So we got 866 times 200, we have 2 zeros, right? So I think this would be 85,600. Is that more or less correct?
That's correct.
Okay. So we have 85,600 R, I forgot my radius, newtons per meter squared. Now you might say, where does the newtons per meter squared come from? We have newtons per meter squared times second. And you know the units of the 30 are 1/2, right? So the second and the 1/2 cancel out, and then what we get is newtons per meter squared. And this formulation makes it a little bit easier for us, because here we're assuming that we already quantify the units of R. I don't want you to get too focused on your units. So what I will say is, if you don't want to do this and you just want to keep carrying the units, you can always do that as well. So whatever makes things easier for you is what works for me. So up to this point, we were able to apply fluids, right? We're able to solve, well, we haven't finished, but we're able to solve Newton's law of viscosity in order to find a relationship between shear stress and distance r from the center. However, that's not everything the problem asks us to do. You know, the problem, it is an engineering-based book, so we are asked to go a little bit beyond fluids and then try to find the torque necessary to rotate the disk. So I'm going to redraw my disk here and try to go over some concepts related to torque. So I have my disk. I am trying to rotate my disk, or I am rotating my disk with an angular velocity omega. And what do I get from that rotation? I know a couple of things. I know that at this point at the edge of the disk, my shear stress will be equal to 85.6 times 10 to the power of 3 multiplied by the radius of this disk. Is that correct? Yes. At any point closer, my shear stress will decrease linearly based on that distance r. Now, at the center, my r coordinate is 0. So what is the shear stress at the center of the disk?
Zero.
Yeah, it's 0. Multiply 85.6 times 10 to the 3 times 0, and I just get 0. So now the question is, how can I take this varying shear stress and relate it to a torque value? Okay? So what we're going to do is we're going to have to go through to our friend calculus, right? And try to do a little differential analysis. Normally, when we're dealing with Cartesian coordinates, our differential analyses typically use squares, right? We use typically squared or rectangular areas. Here is a little bit different because here our coordinate is a polar coordinate that seems to part from the same origin, but in multiple directions. So depending on how you want to do your differential analysis, that's really up to you based on what you've learned on calculus. But if I can make a suggestion, I would say that if we're dealing with polar coordinates, we'd like for our differential analysis to be made in terms of circular differential elements. So I'm going to take an infinitesimally small, and when I say infinitesimally small, I know you've heard this before because I've done it for fluid statics, but when I say infinitesimally small, I mean a tiny, tiny, tiny element. So I'm looking at, this is my center, I'm looking at a tiny, tiny, tiny element, and I would like to get an element where the shear stress is constant all throughout the element. So if I want my shear stress to be constant all throughout the element, that means that my element needs to be at a constant or consistent distance r from my center. So this is a tiny, tiny element. Yeah, imagine that I drew a tiny element, and this element has a thickness dr, a really small thickness, so small that we can't even quantify it or begin to quantify it with numbers. So tiny element dr. So if my tiny element has a thickness of dr, then we should be able to find the area of this element, right? So the area of this element is what? How do you think you can find the area of this element? The area dA is simply equal to my circumference. So that's 2 pi r multiplied by my width, and that is dr. So we have a tiny element with a differential thickness dr and a differential area 2 pi r. This is just the circumference, okay, the circumference around the element multiplied by the thickness dr. So why am I doing this? Like, I'm not really doing this because I want to go back to calculus, right? I'm doing this because really it would be the only way for us to calculate a full torque for this element. So if our goal is to find a full torque for this element, I would say let's first find the force that's acting on this differentially small element dA. So in this differentially small element dA, there is a differential force called dF. And I'm not really sure what that force is, but I do know what the shear stress at that element is. So if we go back to our initial formulation, we know that the shear stress at any point in this disk is equal to 85,600 times R. So if I have a tiny element at a distance R, then my force should be equal to just shear stress times my area of the element. And in this case, my shear stress is 85.6 times 10 to the power 3 multiplied by my distance R. My area is simply my differentially small dA. So if I express this in terms of our differentially small, tiny elements, then I can express everything in terms of my differentially small radius, right? So I get 85.6 times 10 to the 3 R times dA, which we already know to be 2 pi R dr. So what do we get from this? From this, if we were to solve all this, we get 85.6 times 2 times pi. That gives us, let me just pull my calculator. $171.2 times pi. Of course, we can't forget to raise it to the power of 10 to the power 3. And then we have R times R, that's just R squared dr. Okay? So we get this differentially small force. Now, is that enough? No. If we want a differentially small force, that's just for this element, but we need to add all the tiny df's at every element. So not just this tiny element, but at this element, and this element, and this element, and this element, and every single element in this disk. Now that means we have to add up an infinite number of values, but of course, we don't want to do that. Instead, what we're going to do is we're going to integrate. That is correct. Thank you very much. The end goal of this problem is not to find force, right? The end goal is to find torque. So why don't we just skip a couple of steps and just define our torque? We know that torque is equal to a force times a distance, right? So it's a force times the distance. That means that the total torque in this disk should be equal to the sum of all the little forces dFs times the distance r between the center and that little force dF. So torque is equal to force times the distance. So in order to find the torque, I have to add up my force dF times my distance r. So let's go ahead and do that quickly. If torque is equal to force times distance, and that's equal to an infinite sum, then I can say that my torque is just equal to the integral of r dF. Now from here, I think the problem should be solvable. It's just solving this integral, but I'm gonna go over the steps with you. I'm gonna try to be a little bit quick so we can work on other problems. But essentially we have r dF. This would be the integral of r times dF. And for dF, we already have this relationship. So I'm gonna write this down. I have r times 171.2 pi times 10 to the power of 3 r squared dr. Okay? Now from here we can do a little bit of more analysis. Let's get rid of our constants, take them out of the integral. So we have 171.2 pi times 10 to the power of 3. All this is a constant, so we can take it out of the integral. We end up with integral r times r squared times dr. R times r squared is r cubed times dr. What's the integral of r cubed dr? I think this is an easy integral to solve, right? What is that integral?
1/4 r to the 4th power.
That's correct. 1/4 r to the power of 4. But now we need to evaluate this integral, right? We know that r is not an infinite number. R starts at the origin where it is 0, and it ends at the edge where it is 0.150 millimeters. So if our r is a finite value, then we would like to integrate this expression over our finite value of 0, right, to 0.150 millimeters, or just 0.15 times 10 to the power of -3 meters. So up to you how you express it. I'm just going to write it in millimeters so I don't have to write that much. Okay? So keeping in mind your units, if you were to solve this, notice that we only care about the first term. We just multiply 0.150 millimeters to the power of 4 divided by 4 and then multiplied by this constant. So I'm just going to go ahead and solve this. Okay? So, by the way, if you have the answer, you can always feel free to share it with us so that we can move on to the next problem.
Professor, I'd like to just make a smart remark. Your calculator can do integrals.
Oh yeah, it's a Casio FX115, which does do integrals. Thank you. I appreciate that.
I have the same one, so.
It's a really good calculator. I gotta say, it's really a really good calculator.
And as for the answer, I got 60.07 newtons.
60?
Yeah, 68.
68.07?
Yes. Would anybody like to confirm that?
It's torque, so it should be newtons times meters, but I think the number looks about right. Can somebody confirm that?
That's what it says in the back of the textbook.
Okay.
I got the same.
Okay, nice. So it looks like we are in agreement for this value. Is that correct? So we get, I'm going to round it up to 3 significant figures, so 68.1 newtons times meters. So yeah, it's a bit of a tough problem because our fluids concepts are basically found right here. right? And then everything before that and everything after that is just application of previously learned knowledge. But that's essentially how we solve problem 145. I can understand why some students had problems with it. So it does make sense because it's a very long problem. You have your fluid side, and then you have to do a little bit of integrating. But essentially, once you understand Newton's law of gravitation, if you have a clear understanding of how to integrate values, you should be fine.